Good morning, everyone. Welcome to this morning's second session for the Introduction to Optical Fiber Testing for Enterprise Applications. Okay, so a quick overview of what we're going to cover today. So first of all, we're going to do a bit of an introduction to fiber, so the nuts and bolts behind fiber itself. Then we're going to talk about the importance of cleaning and inspecting before connecting in order to maintain good network performance. We're then going to follow up with common tooling you can expect to work with. So they range from visual fault locator, light source and power meter, optic loss test set, and then we're going to delve a bit deeper into OTDRs, not only the operation of an OTDR, how it works, but key things to look at when choosing to purchase one. And then we're going to talk about using and configuring an OTDR to undertake a trace in expert mode. So first up, introduction to fiber. So why fiber? Well, with the ever-increasing demand of higher bandwidths and speed, fiber is able to meet this requirement where traditional copper technologies have traditionally fallen short. Additionally, with newer technologies such as RF over fiber or fiber to the antenna applications, DAS systems, fiber is becoming more prominent and popular inside enterprises to meet these requirements. What are the benefits of fiber over traditional copper? Well, the first and foremost is that fiber is cheaper to manufacture, and obviously reduction in cost is a big driving factor for a lot of new technologies. It's got better transmission properties over longer distances, so longer runs of fiber perform better than, say, equivalent long runs of copper. Obviously, as I mentioned before, it's able to get to those high speeds, which is obviously a driving factor in newer technologies. And some other nice benefits is that it's immune to electromagnetic fields, and it's also immune to lightning strikes, which is obviously critical in private LTE and 5G applications, where obviously active antennas are on top of cell towers and cell sites. So as I'm sure most of you are aware, there's two main types of fiber. So single mode and multi-mode fiber. What are the key differences? Well, on this image on the right-hand side of the screen here, we've got examples of OM1 multi-mode, OM2, 3, 4, and 5 multi-mode, which is has a slightly smaller core, 50 microns as compared to 62.5. And then we've got single mode on the right-hand side, which has a much smaller core of 9 microns. So what does this mean in terms of the actual differences in terms of fiber performance, and why would you use one fiber type as opposed to the other? Well, traditionally multi-mode fiber was used a lot of the time because it was cheaper to manufacture. And obviously cheaper to manufacture meant that people utilize it with there was no requirement to get industrial or high quality light sources and network connections. You could use it with more or less cheaper and lower grade items. That's as opposed to single mode, which was a lot, it's a lot more precisely manufactured, and as a result was a lot more expensive. You need a lot more expensive network infrastructure to mate with it. Nowadays, with improving manufacturing techniques, production costs and manufacturing costs of single mode fiber have significantly come down to the point where there's not really much difference between single mode fiber and multi-mode fiber in terms of cost. In terms of performance, single mode fiber performs a lot better over longer distances, as I'm going to talk about in the next slide. And as a result, applications where multi-mode fiber was traditionally popular have started to fall away, with single mode fiber becoming more and more used, more widely, I should say. So attenuation of fiber. As I mentioned, multi-mode fiber doesn't perform as well over longer distances as compared to single mode. And this is shown in the attenuation or dB of light loss per kilometer of a particular fiber. We can see that for multi-mode fiber, at 850 nanometers of light, you're getting about 3 dB per kilometer of light lost along a fiber as opposed to single mode fiber of 0.3 dB. So what does this mean? Well, it means if you've got a brand new 1 kilometer length of fiber with no connectors, no faults or issues on it at all, you're going to lose 3 dB of light along that kilometer in a multi-mode fiber. And in a single mode fiber, you're going to lose 0.3 dB. And we can see here how that light loss is significantly greater in multi-mode, and we can see why single mode fiber is significantly better for longer runs. On the top table here, we've just got some standards of what is the maximum allowable attenuation. So 3.5 dB is the limit for multi-mode and 1 dB for single mode. Okay, so just touching on wavelengths of light. So wavelengths of light traditionally used for fiber is between 800 nanometers and 1650. 800 to 1300 bandwidth is typically used for multi-mode wavelengths, and 1310 to 1600 typically used for single mode wavelengths. You've then got a band between 1625 nanometers and 1650 nanometers, which is specifically allocated for maintenance purposes only. And I'll chat about that range shortly when we discuss OTDRs and the like later on. Basically though, you can have tooling that's 1625 or 1650 nanometer wavelengths on with a filter, and you can then undertake maintenance tasks and testing without interfering live signals in the fiber, and the live signals in the fiber not interfering with your test set. This graph on the right-hand side of the screen here shows the attenuation levels of different wavelengths of light as opposed to those particular wavelengths. So we can see 850 in the multi-mode area, we've got significantly higher levels of attenuation and backscattering of light, and obviously that leads to the reduction in performance of multi-mode wavelengths as opposed to single mode. As we move up to single mode, you obviously get much lower attenuation, and that, once again, that contributes to the properties of those wavelengths being able to transmit over longer distances. We've then got these two water peaks here, these two peaks in absorption. Now, traditionally, these would occur at around these wavelength bands caused by water particulates in the fiber itself, and that was a byproduct of manufacturing. With newer manufacturing techniques and processes, those water particulates have more or less disappeared in newer fibers, and as a result, these water peaks aren't of big concern in modern fibers. What does that mean for us as users? Well, it means that we can open up these areas which traditionally couldn't be utilized for transmissions due to poor quality to more wavelengths, which means we've got more options when installing network infrastructure and the like. Okay, chatting about connectors quickly. So there's a whole slew of different connectors you can get when working on fiber. We've got four common ones up here. We've got LC, SC, FC, and ST. Now, each connector that you'd utilize or see will be dependent on the application you're working on and where you're working. For example, LC or little connectors, you'd utilize and see little connectors in areas where there's a patch panel and there's a high density or a high number of patch leads running into that one patch panel, and space is at a premium. The only benefit to LC connectors over other ones is they're physically smaller. Likewise, in particular multi-mode networks, you might see ST connectors would be something you'd see quite common, and the like. It's important to note that whilst you've got a range of connector types you can utilize and see throughout networks, you need to understand that all of them can have either a UPC finish polish or an APC polish on the actual fiber interface itself. UPC stands for ultra physical contact or ultra polished connector, and APC, angled physical contact or angled polished connector. Now, the difference between the two is the UPC essentially has a straight cut on the fiber end face, whereas APC has an 8-degree angle on the end face, sorry. What does this mean? Well, it means that APC connectors are slightly better performing, and it's got to do with reflected light. When light hits the APC connector, the light is reflected up into the cladding as opposed to directly down the fiber end face, which means that the reflected light is weaker when it reaches back to the laser source. Important thing to note is that you can only connect APC connectors to other APC connectors and UPC to other UPC connectors. If you try and connect an APC connector to a UPC connector, whilst you'll probably physically be able to connect them together, what you're actually going to do is crush the end faces. And remember that these are glass, so they're very, very delicate. If you push a UPC connector on an APC connector, the APC connector is going to try and cut a groove or dig a groove or gouge into the UPC connector, and the UPC connector is going to crush the end face of the APC connector, obviously permanently damaging both connector end faces, and as a result, you're going to get a high loss event when those two connectors come together, potentially even bringing down your whole fiber link. So how do you identify the two? Well, if you look very closely at the end of the fiber, you might be able to see the different polish that you've got on each end face, but convention dictates that blue connectors like these ones in the image are UPC and green connectors are APC. So just remember that for making sure that you always connect green connectors to green and blue to blue, which is actually UPC to UPC and APC to APC. Okay, so we've talked about the nuts and bolts of fiber itself. Let's move on to talking about improving network performance. So around about 80% of faults in the field are caused by dirty connector end faces or damage and scratches on connector end faces. And how do these occur? Well, they occur when people aren't inspecting and cleaning before you connect. So we've got a little flow chart that should always be followed whenever you're connecting any two pieces of fiber together, whether that's your launch lead to your OTDR, your launch lead to your patch panel, two patch leads together. Whenever you connect two pieces of fiber together, whether it's permanently or for a 3-second test, you need to inspect before you connect. So the flow chart we follow is you inspect it with your inspection probe and you ask yourself, is it clean? If it's clean, yep, you can go ahead and connect. If not, here's an example of a dirty end face. You would need to clean it and then re-inspect it and ask yourself, is it clean again? Obviously hoping it's clean and going ahead and connecting. If you connect two end faces of connectors that are dirty together, not only will the dirt contaminate both sides of it, but pushing a piece of dirt between two pieces of glass on such a small area puts down phenomenal force on it, and that can lead to scratches and pitting. And obviously when scratches and pitting occur, you actually have to replace the connector. You can no longer clean the scratches and pitting off. So moving on to our next example here. So we've got two connectors coming together inside an adapter. UPC connectors, because obviously it's a vertical finish. So we've got a piece of dirt that's getting stuck between them. Second connector comes in, and we can see that the light passing down the fiber is getting obstructed by the dirt and getting a significant amount of back reflection down the fiber. We can see on the right-hand side, a small amount of the light has passed through the dirt and is proceeding down the fiber. Now, because the light coming out on the right-hand side is significantly reduced to the light on the inside, sorry, on the left-hand side, that means that if this is perhaps a long piece of fiber, that piece of, or that portion of light may not make it to the end of the fiber, and essentially your whole link will no longer work. Additionally, perhaps it's a shorter link of fiber, and you might have 2 or 3 dirty connectors in a row. Or 2 or 3 dirty connectors in a row would have a cumulative effect, and once again, your link could come down. So it's important and highlighting the importance of inspecting and cleaning before you connect. So how are we doing this cleaning? Well, there's 2 main common solutions that most people utilize when cleaning connector end faces. First one is the cleaning pen, and you simply remove the cap, connect the pen to the end of the fiber, male or female side that you want to clean, and you simply click the pen down and it'll clean the end face. It takes about 2-3 seconds, so there's not really an excuse for not utilizing something like a cleaning pen. On the other hand, you've got what's called a cleaning cassette. In order to utilize a cleaning cassette, in this case, you would pull the orange tab to the right-hand side, which would expose a clean piece of cleaning fabric, and you would then rub the connector end face, as per the bottom image, on the exposed piece of cleaning fabric, remembering to rub the connector in one direction only. And when you rub the connector, every time you complete a rub in one direction, you move it across, so you're rubbing it in clean parallel tracks, so that every time you wipe the connector, it's essentially on a clean piece of fabric. Now, when you release the orange tab back to the left-hand side, when you then pull it again to the right, it exposes a new and clean piece of fabric. So every time you clean a new connector, you've got a clean piece of fabric for it. Each one of these products is a disposable or consumable item, so there's no reason not for using it, and they're extremely cheap. So each one you get probably 8 to 900 cleans per product, and it's about $100 to get them. So they're very cheap, and you should always be utilizing them whenever you do that, and it will significantly improve your network performance and reduce your troubleshooting, your time spent troubleshooting. So here we've got some examples of dirty connector end faces and connector end faces that have been cleaned not using the proper technique. On the left-hand side here, we've got an example of a dirty connector face. Just like your windscreen of your car, if there's dirt and grime all over it, light's going to have a hard time passing through it, and as a result, degradation in network performance. Just highlighting here that we can see this is a single mode fiber. So we've got the cladding on the outside, which is this gray area, and we've got the core of the fiber, it's very small end face here. So any dirt, particularly over this area, is going to have the greatest effect on your network performance. Moving on to the right-hand side, we've got an example in the top left corner of a connector end face that has been cleaned and inspected properly and correctly. We can see how clean and clear that is, and how much easier light's going to have passing through that particular connector as opposed to a dirty one. Now, the other 3 examples here are people who have tried to clean their connectors, but they've done something wrong. And the first one is they've tried to wipe it on their shirt, and they can see that by not using the correct tooling or techniques to clean your fiber end face, they've actually made it significantly worse than if they didn't clean it at all. So big factor there, make sure you use the proper techniques and tooling, because wiping on your shirt as well has the chance of inducing more dirt onto the fiber end face, and by rubbing it on something that's not clean, you could drag that dirt across the end face, once again scratching the end face, which will cause you to require to replace that particular connector or patch lead. The bottom two images here show your first connector is someone's actually cleaned it using the proper technique, say a cleaning pen, but the alcohol residue is not dried properly for whatever reason. So this here highlights the importance of, even though you do clean it, you need to inspect the end face following cleaning to ensure that something like this doesn't occur, because now the alcohol, which is typically used to clean the connector end face, is now impacting the passing of light through that connector. And the final image here, we've got an example of someone cleaning the connector properly, but they haven't cleaned their patch lead or launch lead that they're connecting into that female connector. As a result, the patch lead or launch lead is dirty and it's transferred dirt across onto the dirty connector. So this highlights the importance of cleaning and inspecting both your male and female sides of connector to get a good connection. So how are we doing this inspecting? Well, the use of fiber inspection probes. It's important to choose a fiber inspection probe that meets your requirements, and there's a whole variety on the market. So the first and foremost one that most people look at is a probe that has both that is auto centering and autofocus. And that's mainly used in order to significantly reduce your time spent testing. Other considerations to think of when you're looking at getting an inspection probe is, hey, do you want one that works with your particular OTDR? So in the case of Viavi, you can look at a P5000i inspection probe, which will work with any of your Viavi OTDRs. Additionally, you might want to look at, say, specialist requirements. And are you inspecting special type of connectors? For example, MPO connectors. For those of you who don't know, MPO connectors are essentially a connector where multiple fibers run to that connector interface, anywhere from 8 to 32 fibers. So you can get specialist tools like the Viavi Sidewinder to inspect all of those fibers simultaneously, once again with autofocus and auto centering capability. Now, the reason why autofocus and auto centering capability is such a big consideration when you're choosing the inspection probe is the time you're going to spend testing and inspecting fiber end faces. On a normal OTDR trace, remembering that we have to always inspect before we connect, you have to inspect, obviously, when you connect your launch lead to your OTDR, there's 2 inspections, your launch lead to your patch panel, two inspections, your patch lead to your far end, there's another 2 inspections, and then obviously reconnecting the network once you finish testing, that's at least another 4 inspections if everything goes right the first time. If you're saving 20 seconds from using an autofocus auto centering probe compared to a probe that doesn't auto center autofocus, you're going to save yourself 200 to 300 seconds or 4 to 5 minutes every time you do an OTDR trace, which is a significant time saving. So just summarizing on fiber cleaning and inspecting, it's absolutely paramount and critical that you always inspect before you connect, or clean inspect before you connect. Ensure that cleaning is carried out using the correct techniques. If you don't use the correct techniques or use improper techniques like wiping the shirt, you could either make it worse, or you can also cause damage on connector end faces, which will obviously then require replacement and troubleshooting at a later point in time. And it's critical that you also utilize a suitable inspection probe for your testing requirement. And the reason that is not only do you want to save yourself as much time as possible, but if you make inspecting fiber end faces more difficult than it needs to be, then technicians and tradesmen may get lazy and don't think it's worthwhile, and they're not going to do it as much. So make sure you get a probe that's very easy and suitable for your team to be using. Okay, so that sums up fiber inspection. Now we're going to move on to basic fiber testing tools. So today, as mentioned before, we're going to go over the visual fault locator, light source and power meter, optic loss test set, and then we'll go a little bit deeper into OTDRs, or optical time domain reflectometers. First one we'll look at is VFLs, or visual fault locators. In very crude terms, think of a VFL as just a red laser pen. You can use it for 2 main things, and the first one is fiber identification, and the second one is basic fault finding. In fiber identification, an example of this would be you have 10 patch leads running out of a wall recess. They go into the wall recess, down the hallway or corridor to a patch panel, come out of the wall recess by the patch panel, and you want to identify which fiber you're connecting to which particular port. At one end of the fiber, you would connect the VFL, turn it on, walk down the other end of the hallway by the patch panel, and you identify the fiber where the red light is coming out, remembering not to look down the fiber itself, but to look at the fibers against your hand or on the floor for that red light. Obviously, this enables you then to connect it to the relevant port or position that you want it to. So that's the first use case for it. The second use case is as per this lower image just here on the right-hand side. So what we've got here is the VFL connected to a patch lead, and you can see that this patch lead has a break in it. So by utilizing a VFL, we can actually identify and clearly see physical breaks in fiber. And that's done a lot quicker and a lot easier than using a whole range of other test and measurement gear. So the pros of the VFL is that it's very cheap and easy to use. So once again, around about $100 will get you a VFL laser pen with range of about 5 to 10 kilometers, which is plenty for a VFL. The cons of using a VFL is that you need to have a view of the entire fiber. If this scenario where we're trying to troubleshoot with the VFL was in that example I just provided before, where the patch leads run into the wall recess, if there's a fault behind the wall recess, you're not going to be able to identify that or see that. So you need to have a visibility of the entire fiber you're testing. Next test sets we'll chat about are light source and power meters. So in basic terms, a light source and power meter essentially check the continuity of a piece of fiber. The light source, a light source or laser source is simply a device, and all it does is generate wavelengths of light at a particular wavelength dependent on the model you get. So traditionally you can get a single mode unit or a multi-mode unit. Single mode unit obviously can generate say 1310 or 1550, and multi-mode 850 or 1300 nanometer wavelength light. On the other end of you've also got a power meter, and a power meter, all the power meter does is detect how much light is arriving at that given power meter. Most power meters have the capability to do both single mode and multi-mode wavelengths, but obviously make sure you get a suitable one for your light source when you purchase a unit. How do you use them? Well, before you take them out in the field and use them, or before you're about to use them in the field, I should say, what you want to do is connect a patch lead or a short piece of fiber, maybe 1 to 2 meters between the two units. And what you're going to do is a quick serviceability check and make sure that they're roughly calibrated. So when you connect the patch lead between them, just as we are in the picture, you want to set the light source, as an example, 1310 nanometers, and then you want to get a reading on your power meter on the other end. And essentially you want to make sure that you're getting pretty close to 0 dB of light loss over that given length of fiber. So it's because it's so short, and we only want to make sure that there's almost no light loss over that given length. If it's pretty close to 0 amount of light loss, then we've got a serviceable light source and power meter. We can take that out and use that on the fiber we actually want to test. When we're testing the fiber in the field, or that we want to test, you do this by connecting the laser source to one end, once again turning on 1310 or 1550, whatever wavelength you want to test at. And then you walk down the other end of the fiber, connect the power meter. And the power meter will give you an indication of the light lost across that particular link. Remembering, there's a couple things you need to remember here. First of all, the light source and power meter is not going to tell you if there's a fault. You as the tradesman or technician need to interpret the results given by the power meter, and then determine if that's a serviceable link or not. And an example would be, you're testing a 100-meter long piece of fiber. If the power meter says that you've lost 10 dB of light, then you need to identify that that's unserviceable. Whereas if you're doing a test on, say, a 10-kilometer long fiber, and you've got 5 dB worth of light loss, then you could interpret that as, hey, that's a serviceable fiber, remembering to factor in whether it's single mode or multi-mode wavelengths and so forth. So the pros and cons. So pros, very cheap to purchase. You can get a light source and power meter pair anywhere from $1,000 to $4,000, depending on the wavelengths and sort of extra accessories and features you want. The cons, it's not able to identify the location of a fault, and you need to interpret the results yourself. So the technician needs to have a little bit of skill and understanding on what they should be looking for. The next con is you need to access both ends of the fiber. Now, in the example I gave of a 100-meter long piece of fiber, that's not too big of an issue. But when you start talking about links that are 5, 10, 15 kilometers long, being at both ends of the fiber can start to be a hindrance, especially if you have to drive between the two. Okay, next piece of tooling we're going to chat about is Optical test set. So an Optical test set, think of it essentially as a power meter and a light source combined into the one unit. So up the top, we'd have a laser source or light source port and a power meter port. Now, Optical test sets are typically always utilized in pairs, and that enables bidirectional testing capability. An example of where this would be a great use, or a great use case of this would be, say you're doing testing in an apartment building. The main patch panel for the building is in the basement, but you're running tests up to the top floor. Rather than with say a traditional light source and power meter, you'd have to walk between the basement and the top floor continually to take readings off your power meter on the top floor. What you can do is, before you start, you set your remote unit up on the top floor, and configure it for bidirectional testing. connect it up, and then you go down to the basement where you can undertake all your testing from the unit in the basement, getting power, changing your wavelengths, getting indications of power lost across particular links and so forth. And then once you finish your testing, you can go up to the top floor and connect your remote unit. So the pros of this one is obviously bidirectional capability, provides you time-saving factors, so speed of testing, and also there's perhaps no requirement for a second person to assist you on the far end of the fibre. You can have it configured back in the workshop by senior or more experienced technicians to set pass-fail limits. So when you provide them to, say, junior technicians out in the field, they're just looking for a clear pass or fail indication. And because you're getting those clear pass-fail indications, it actually reduces the chance of human error as well. The cons of the optic loss test set, once again, is it doesn't identify a location of a particular fault. And once again, you need to access both ends of the fibre, which can be a hindrance on very long runs. Okay, so that sort of covers the basic tooling and test equipment we use. Now we're going to chat about optical time domain reflectometers, or OTDRs, a little bit more in depth. And these are probably some of the more comprehensive tools most fibre technicians will work with on a daily basis. So OTDRs come in many different form factors and with a whole range of options, which will obviously need to be customized depending on the particular application you're working on. So we can, in most common terms, like some of the common options that you can look at is a VFL or power meter. So that's combining with some of those tools that we just discussed, combining them into the one unit. You might also need capability for bidirectional OTDR testing. Say if you're doing testing on a pond and want to do some testing through some splitters, would be an example of that. You want something that's compatible with inspection probes that we were discussing earlier. Do you require a remote control unit, say via your phone or PC? Do you need automatic report generation? And for more advanced testing in some of the large enterprise customers, maybe they're also looking at Ethernet and network testing capability up to 100 or 400G, depending on what you're working on. So choosing an OTDR is a pretty big decision, and there's a few things that need to be considered when looking at it. The first and foremost is your wavelengths that you need to test on your network. So you can look at OTDRs that only test single mode. So you might say want a 1310 or 1550 module, or perhaps a module with 1490 and 1625 as well. Do you need a multi-mode module? So 850, 1300. You can get OTDR modules or OTDRs that do both single mode and multi-mode. Or you might need an OTDR that could do, say, 5 wavelengths, depending on your requirement. So knowing what you're testing on your network is the biggest and probably most important decision. The second pretty big decision you need to know and understand is dynamic range. Now I'm going to chat about dynamic range shortly, but in very crude and basic terms, dynamic range is how far the OTDR can shoot a trace. In very basic terms, but I'll explain that further shortly. Budget isn't a big consideration as well. And the only reason budget's such a big consideration is there's such a variation of OTDRs you can get, with basic entry-level models sort of starting at about $2,500, up to full-blown network testers with Ethernet testing capability. You're sort of at the $30,000 to $35,000 mark. So big range in prices that you can go between, and having an idea of how much you want to spend really helps narrow down what's available to you. And then finally, as we sort of discussed just before, the wide range of options that you require, whether you want to combine VFL, power meters, remote access, and so forth into the one tester, obviously also will vary the units that perhaps are of your interest, and obviously impact budget as well. If you're sort of thinking about getting a new OTDR and you're not too sure where to get or where to start, on the Vicom website, there's an OTDR selection guide, which can step you through a couple of the basic questions and start getting you in the right direction for which particular OTDR will start to suit your needs or requirements. So we're just going to touch on the principles of OTDR operation now, and there's a few things that a lot of customers get confused about or don't quite understand when they start doing their traces. So what we've got here is a basic setup for an OTDR undertaking testing. We've got our OTDR on the left-hand side of the screen. We've got our launch cable or launch lead installed between our OTDR and our first connector. We then got our fiber under test, and we've got our receive lead or receive cable on the far end. Now, when you hit start on an OTDR, the OTDR emits a pulse of light. That pulse of light then moves down the fiber. Every time it gets to an event, which is a connector, a splice, a break, anything that occurs along the fiber, a portion of light is then reflected back to the OTDR, which the OTDR detects. Now, the OTDR is continually measuring these, or measuring these received parcels of light back, or packets of light back, and they're measuring three things, or working out three things. The first one is the power of the reflected light. So what's the power level of the reflected light? They're also calculating the time. So the time it's taken for that pulse of light to go from the OTDR to the event, and then that reflected portion of light back to the OTDR. And they combine that with the known speed of light through fiber. And that enables us to calculate how far away a particular event is. So in this case, how far away this first connector is. And because it knows the amount of light being reflected back, it also is able to calculate how much light, because it knows how much light is reflected back, it knows how much light is continuing down the fiber, and can give us an indication of that as well. So how big this event is. Obviously, that portion of light then continues down the fiber, and it'll continue to do this right along the fiber. So we could be continuing to get reflected portions of light back to the OTDR, which is then calculated and combining in a trace, which I'll show you shortly. Just quickly, why do we utilize a launch cable and a receive cable on an OTDR trace? Well, an OTDR, no matter how good an OTDR you get, your OTDR is going to have what's known as an OTDR dead zone. And essentially an OTDR dead zone is the very first portion of fiber under test your OTDR can't see. And that's caused primarily by a large amount of backscattering light occurred when the initial pulse is released from the OTDR. What this means is if we didn't have a launch lead in this position, where essentially the very first connector in the fiber under test is going to fall into that OTDR dead zone, which means that we won't be able to check the serviceability of the very first connector and the first few meters of the fiber under test. So in order to enable us to see that very first connector, we use a launch cable or a launch lead, which is essentially a tool, you keep in your toolbox, and it simply just removes the OTDR that little bit further back from the network, so then we're able to see and inspect that very first connector in the fiber under test. Likewise, a receive cable, which is identical to a launch lead, they're interchangeable. A receive cable enables us to check the serviceability of that very final connector. If the receive cable wasn't there, we wouldn't be able to see if that last connector is serviceable or inserviceable. And that's why you need to utilize a launch lead and receive lead in order to check the very first and very last connectors in your fiber. Okay. So as I mentioned before, an OTDR sends a pulse down a particular fiber. Now, it doesn't just send one pulse, it's sending thousands of pulses and averaging all of the results together in order to get a very clear and precise image of the entire fiber under test. When we've got our OTDR conducting those thousands of pulses, averaging those thousands of pulses of light, this is the result that we're getting here. And this is an OTDR trace. This OTDR trace lines up pretty well with the OTDR trace that we've just explained here with this fiber under test. And we can see that at each connector, there's a reflective event, and the reflective event is shown by this spike of light coming here, which is obviously being reflected back to the OTDR. We can see then, because some of the light is being reflected back, there's also a drop in the loss when the light levels after the connector. And that's indicated by this step here. So we've got power or loss here and distance from the OTDR along the bottom. And we can see when it gets to a connector, there's a reflective event, and then there's a drop in the amount of light after that. And at each connector that occurs, what you'll notice is that the splice is actually a non-reflective event. So you've got two main types of events, and that's a reflective event and a non-reflective event. And in a non-reflective event, there is no reflected light back to the OTDR. Just a portion of light is lost due to the splice. And obviously down the far end, we've got two reflective events for these two connectors as well. Just a quick point, this angle of the OTDR trace here is caused by the fiber attenuation that I was talking about at the start of the presentation. So remember I mentioned that single mode fiber loses 0.3 dB of light loss per kilometer. Well, that's shown on your fiber trace by the angle which is going down here. So even when there's no connectors or no issues with the fiber, it's a clean piece of fiber, we're still losing power over distance as the light tries to pass through the glass. Now, sometimes in shorter traces, you won't be able to identify that downward trend, and that's because the fiber or the trace is too short to identify that. All right, so we talked about OTDR dead zones before. Now we're also going to just quickly mention event dead zones. And an event dead zone, like an OTDR dead zone, is essentially a dead zone immediately after a particular event along a fiber. So you won't be able to see any events occurring immediately after an initial event. And the length and size of your event dead zone is essentially determined by the pulse width of your light. And I'll chat about pulse widths of light shortly. All right, dynamic range. So dynamic range is the parameter defining the maximum optical loss an OTDR can analyze from the backscattering of light. In very basic description, it's how far an OTDR can shoot a trace. And we do sometimes have difficulty explaining this to some customers, that whilst having a high dynamic range does enable you to shoot a longer distance in terms of kilometers, there are some issues in that thinking. And I'm just going to try and cover a couple of the issues in that thinking shortly to help better understand how dynamic range and distances you can shoot a trace with an OTDR overlap and work together. So here an example, we've got the same fiber under test, same number of connectors and so forth. We've got a little bit more information this time though. We've got a 20 dB dynamic range OTDR here on the left-hand side. And once again, like I said, same setup. We've got our launch lead. We've got our connectors on our network, all with 1 dB of light loss for simplicity, and a splice with 0.1 dB, and then 2 connectors down the end again. Now we've got a 10-kilometer long fiber. And remember, I said at the start, for single mode fiber, you can expect to see about 0.3 dB of light loss per kilometer. So for 10 kilometers, that's 3 dB of light loss. So over this entire 10-kilometer link, with all these connectors and splices factored into it, we've got 8.1 dB of light loss over that particular link. Now we've got a 20 dB dynamic range OTDR. So because we've got a 20 dB dynamic range and there's only 8.1 dB of loss, we're able to see the entire length of the fiber and all the events along the fiber. So if the dynamic range is greater than the loss, you're able to see the whole fiber. Now let's go to the next example. Once again, we've got a 20 dB dynamic range. We've got the exact same network setup, all the same loss levels, but we've now got a 70-kilometer long fiber, so considerably longer. And because it's considerably longer, once again, 0.3 dB per kilometer, we've got 21 dB of light loss over a 70-kilometer long link. So our total loss for the link is 26.1 dB. We've only got a 20 dB dynamic range OTDR, which means that our OTDR is not going to be able to see the entire length of the fiber. The trace on the OTDR is essentially going to fall into the noise floor before the end of the fiber is reached. So on that trace that we saw earlier, that graph is essentially going to run into the floor before we can see the entire length of the fiber. And we're not going to be able to identify all the events towards the end of the fiber. Now in this scenario or this situation, if we had a 30 dB dynamic range OTDR, because that 30 dB dynamic range OTDR would be greater than the light loss, we'd essentially be able to see the whole length of the fiber and all the events along it. So 30 dB dynamic range in this scenario, we'd be able to see 70 kilometers of fiber. Now keep that in mind, because now we've got a 30 dB dynamic range OTDR and only 40 kilometers of fiber. So we've got 30 kilometer shorter piece of fiber, but the connectors along the fiber now are significantly worse. So obviously no one's been cleaning or inspecting before they connect. We've got damage from hauling, perhaps maybe someone's put a zip tie around a fiber, which obviously has crushed the glass. Splice is a little bit worse, and obviously these two connectors here haven't been properly inspected and cleaned before they've been connected again. So we've got a 40 kilometers, so we've got 12 dB of light loss. But because we've got all these extra events here, we've actually got, our total link is now 37.5 dB of light loss with our 30 dB dynamic range OTDR. What does this mean? Well, even though we've got a higher performing OTDR, and in the previous example, a 30 dB dynamic range OTDR could do 70 kilometers, it cannot complete testing on this 40 kilometer link because the network performance is too poor. So once again, this highlights a couple of things where just because you get a high dynamic range OTDR doesn't mean you can shoot a further distance. It's also dependent on your network performance and how well your network's being maintained. So all of these inspecting before you connect, as we discussed before, have given you cumulative buildup. If these were all 1 dB events from being properly inspected and connected, you'd still be able to see the entire length of the fiber because we'd save ourselves 2, 4, 6, 8, 10 dB of light loss. It would be under the 30 dB dynamic range limit. So hopefully that clears up dynamic range for some people. Okay, so we're next going to just quickly talk about undertaking a trace on an OTDR. So the example that I'm going to run through today is on a Viavi MTS 2000 OTDR with a single mode tri-wave OTDR module. So 1310, 1550, 1625. Whilst I'm giving an example on an MTS 2000 for Viavi, all the GUIs on the MTS 2000, 4000, 5800, 6000, so on, are all more or less the same. So you should be able to follow the same steps, pressing the same buttons on the menu and so forth. Now, if you've got a different brand OTDR, you will have very similar settings and configurations you can make, but where they're located in your particular menus, you might need to find yourself, unfortunately. All right, so when you turn on your MTS 2000 or any Viavi OTDR, this is essentially the home screen you're going to be presented with. As the OTDR modules on Viavi are or changeable, the mainframe settings that always stay on the unit are shown up the top, and the OTDR module ones, which change with the OTDR module you got fitted, are shown down the bottom. So up the top, we've got our remote access. If you wanted to remote control your OTDR as an example, or upload results to the cloud via Strata Sync, they're shown in the top half. Whereas your OTDR capability in your expert mode is shown down here, which is what we're going to go through today. Just knowing that if you're a little bit nervous or novice on what you're doing, you probably want to go in the smart test mode, which is essentially like an OTDR wizard. It'll ask you 3 or 4 questions and it'll start running a trace for you. So it's very automated, that one. So today we're going to go through expert OTDR. So when you select the expert OTDR mode, this is the screen that's going to greet you with. What it's going to show on this screen is the last trace that you've conducted. Now, if you've got a brand new OTDR, this OTDR screen will be black or blank. The screen is split up into 3 main areas. So the first one is your primary trace view. On the right-hand side, we've got our first lot of menus. So up the top, this is a button that lets you switch between trace view or smart link mapper, which essentially replaces the traditional trace with small icons. I'll show you that screen shortly. The zoom and shift button, which enables you to obviously zoom in and shift the trace around to get a better view as required. Next option lets you select and move cursors A and B as required. Fast report here enables you to generate PDF reports as required to provide to customers or to management as needed. And the bottom 2 options are simply more advanced settings and so forth. The third portion of the screen is down the bottom here, and that is a summary of each event along here. So we can see event 3 is shown, event 3 is highlighted, and it gives you a summary of event 3 of what's going on. Remembering that if you've got say a Viavi MTS 4000 or 5800, something with a larger screen, this portion of your screen is going to be larger. You can scroll up and down through your results through the little scroll wheel on the right-hand side. Now we want to configure a new trace. So what we're going to do is press the setup key here. Remembering that if you're on a fully touchscreen OTDR variant, then you're going to have a soft key either on the top or bottom of your OTDR, and you just need to select it. So choose setup, and we get brought into the setup screen. Once again, down the right-hand side, our options for menus have changed, and we're going to go through the acquisition screen. So this is the nuts and bolts for configuring your OTDR mode. The first thing you need to do is select if you're undertaking testing on a point-to-point network or on a PON, a passive optical network. Now in enterprise applications, 9 times out of 10, you're going to be working on a point-to-point network, which is more or less a straight piece of fiber. Maybe you've got connectors and splices and so forth along it, but it's more or less one straight line. When you're working in a PON, or what is a PON? Well, a PON's a network where you've got not only single-stranded fibers, but you've also got splitters and so forth in it, which is splitting one fiber into many. Now, by selecting it on PON, you're going to tell the OTDR to be on the lookout for splitters, which are very high loss events. If you, say, undertook testing on a PON just using point-to-point mode, what's going to happen is the trace is going to get to a splitter, which is a high loss event, and it's going to think that high loss event is simply the end of the fiber. It's not going to keep on trying to look beyond that. When you turn it to PON, it'll be on the lookout for splitters. It'll identify when it reaches a splitter, and then it'll try and continue to read the trace beyond that particular splitter. Remembering that best practice, if you're doing testing on a PON, is to undertake your testing from the furthest most point from the core and shoot the trace towards the core, as opposed to starting or running your trace from the inside of the network out to the most remote parts of the network. And that's got to do with how the light passes through splitters. Okay, the next option you've got is for your laser or wavelength that you want to utilize for your testing. It's best practice and recommended that for your use of testing, you combine 2 wavelengths with the greatest distance or greatest difference between them. So in this case, it would be 1310 and 1625. And the reason for that is that gives you the best chance and most accurate readings of picking up macro bends and so forth in your tests. Remembering that the wavelengths that you might need to choose or utilize could be stipulated in internal company policies or perhaps particular standards that you need to meet. So keep that in mind when you're choosing your wavelengths, as well as what's required by the enterprise you're working for. Next option is acquisition mode. So today we're going to go through obviously manual, which gives you full control of range, pulse, and resolution settings. Auto mode automatically adjusts the range, pulse width, and the resolution for best results in your trace. And then we've got another setting here for smart acquisition. Now, smart acquisition combines both short and long pulses in the one trace, which enables higher or more clarity on longer range traces, where it's enabling the benefits of the shorter pulse width and combining them with the benefits of the longer pulse width as well. So I'll chat about pulse widths shortly, and you'll be able to understand why short and long range pulses are different and the benefits of each. So next is just range, just getting a rough estimation of how far you're going to be shooting a trace, remembering that if you want to configure the units that are shown here, you can do it under the analysis menu, which I'll show you shortly. Okay, so pulse width. So it's important to understand the fiber that you're testing and how a different pulse width will give you better or worse results depending on that. As a rule of thumb, the shorter the fiber you're testing, the shorter the pulse width you want to utilize. But you want to use as short a pulse width as you possibly can because it gives you a much higher resolution trace. On the other hand, if you're doing a trace on, say, a very, very long fiber, maybe 80, 100 kilometers, you want to be utilizing a much larger pulse width because the pulse of light itself is going to have more energy and it's actually going to be able to make it to the far end of the fiber. For example, if you're doing a 80, 100 kilometer long pulse and you're trying to use a 5 nanosecond pulse, there's just not enough light or power in that light for it to make it to the end of the fiber. So you're not going to be able to see probably after the 2 kilometer mark, 3 kilometer mark, something like that. It's all going to be or the light's not going to be able to return back to the OTR. It's just not going to be strong enough. So here we can see the differences in pulse width and the importance of selecting the most appropriate one for your application. So here, this is the exact same trace run multiple times with varying pulse widths. We can see a 10 nanosecond pulse, how high resolution it is. We can see how clear and accurate each of the each of the event locations are. As the pulse width increases and grows, we can see that these events are getting wider and wider and less, they're not as precise. So the resolution that we're getting on the trace is falling away as we increase the pulse width. We can see here that on a 10 nanosecond pulse, the event dead zone is almost negligible, like it's very, very small indeed. Whereas on a 3 microsecond pulse, this entire area here is an event dead zone, which means that if an event was to occur immediately following this particular event or this particular connector, say, then we're not going to be able to identify that on a 3 microsecond pulse. We'd be missing entire issues with fiber. So that's why it's important to utilize the smallest pulse width that's going to enable you to test your entire length of fiber. Now that smart acquisition mode I mentioned before actually combines pulses of all pulse lengths or varying pulse lengths together. So then you can get the benefits of high resolution towards the OTDR. And as you get further away from the OTDR, you're falling away on the number of pulse widths you can utilize, and you're still going to get details on the far end of the traces if you would utilizing a 3 microsecond pulse to begin with, but you're going to have a better resolution of your trace closer to your OTDR. Next one, just further details on customizing resolution of your trace. Acquisition time. So as mentioned before, rather than just sending out one pulse of light, the OTDR is actually averaging thousands of them over a given time frame. Now, it's important that dependent on your pulse width, you select an appropriate time or acquisition time. The smaller your pulse width, obviously the quicker it's going to take for a pulse of light to undertake a trace. So you can utilize these smaller acquisition times. If you're doing a 10-second trace on a fiber that's only 500 meters long with a 5 nanosecond pulse, you're going to get stacks of results for your OTDR to average in that 10-second time frame. Whereas if you're doing a 3 microsecond pulse over a really long fiber, you're going to need to increase the time to maybe 90 seconds or 2 minutes to ensure you get a really accurate trace and get enough averages back to get a clear picture of the fiber. OTDR connector test. So an OTDR connector test is pretty much a serviceability thing, and what you're doing is you're checking the continuity or serviceability of the connection on the OTDR and removing that from the network on the test. So if you're experiencing troubleshooting and you're not too sure what the issue is and you want to make sure that the OTDR is serviceable, what you can do is you can set the OTDR connector test and make sure that the connection from the OTDR to the fiber under test or to your launch lead is serviceable. And here you can choose yes and continue with the trace, or we just want to check yes and abort, which would be just, let's just check the OTDR for serviceability, and then I don't want to run a trace. And the reason that's important is if you've got it for 3 wavelengths on 3-minute acquisition times, you're going to have to wait 9 minutes if you click yes and continue there. So that's why there's a yes and abort function. And finally, the last setting on this particular menu is for launch cable. Now, you always want to, or you should always be utilizing a launch and receive cable, as I mentioned before, the benefits of doing that, and that's in order to get a full picture of your fiber. By selecting these on your Viavi OTDR, what it's actually going to do is enable you to see the launch lead on your trace, which I'll show you very shortly. So that's your acquisition menu. Just quickly on your alarms menu, most of these alarms are set pretty well already, but make sure that you customize your splice loss and connector loss alarms to meet your given enterprise standards or whatever you're testing against. And that way it'll automatically identify faults and issues when you conduct your trace. This is the menu where we adjust them, and I'll chat about these shortly and how it impacts your final results on your reports and so forth. Analysis menu. Here's where you change your section attenuation units. dB per kilometers is pretty safe, but distance unit is probably a big one that we want to be changing, and that's feet here. We obviously probably want to change that to meters if we're working in metric units, which most people probably would be. The link cable option on this is probably a very important menu to ensure that it's filled out correctly. And the reason it's important that it's filled out correctly is these are the results that are automatically going to populate on your PDF report when you complete your trace. If you input the wrong information in here or forget to update the information in here, when you generate a report at the end of your trace, it might have inaccurate or improper information. So making sure that you get your locations right. So perhaps, I don't know, Sydney CBD to Parramatta CBD, making sure that your trace is running in the right direction. Your particular cable ID is numbered properly, and your fiber number in particular done, so that you're very aware of what fiber is going to what, and you can identify the report clearly at a later point in time. Because if you've done 20 or 30 traces in a day and your report's all jumbled at the end, it's going to be very, very hard, if not impossible, to separate which particular fiber goes with which particular report. Additionally, on the right-hand side, we can input information about the technician doing the job. Maybe there's a job or contractor ID number and so forth. We can populate all that information there, so that when the report happens, it automatically generate it, automatically save it. You don't need to do anything with it. You can just send it to your customer or to your management team, however you require, either via USB or through Strata Sync through the cloud. So here's the next menu for file is simply your saving instructions and location. So directory, do you want to save it on a USB, on the OTDR hard drive, maybe a portable hard drive and so forth. Your file naming convention, and you can see file content for one trace, so you can configure that to more if you would like, and we're auto storing it or auto saving it after each trace. You're saving your report as a PDF, so I think there's another option for Excel spreadsheets. And this option down here is a handy one to tick to yes, especially if you're using something like a P5000i inspection probe with your OTDR. So you can automatically save the inspection end phases of connectors into your PDF report as well. Okay, so we've configured the OTDR. We want to hit start stop to start our trace. Just press this green button on the MTS 2000, remembering that on your touchscreen variants, there'll be a soft key on the screen that you can touch. First thing it does is it does a connection check to make sure that the connection of the fiber is serviceable. If this connection was bad, it'd be down here on the red end, and obviously it won't let you undertake the trace. You need to rectify that fault firstly. So maybe the connector's not seated properly, or you haven't cleaned and inspected it before you started your testing. Once the trace starts to carry out, we can see that we've got 20-second time, and on a 5 nanosecond pulse, as indicated by up here, it's done 94,000 pulses of light in that 10-second or 11 seconds so far, sorry. And it's starting to average it, and we're starting to get a clear idea of the fiber under test. Once it's complete, this is the final view. So remember that we selected to show our launch lead. So here we go, this little icon up here identifies the launch lead, and this other one over here identifies a receive cable. So now we know that our particular fiber under test is only in this area between events 1 and 6. This little icon here shows our end of fiber or end of cable under test. So after the launch lead, that will show. Now this particular view can be a little bit hard to interpret all your information and it's not showing very nicely. So what we do is up here, we're going to go through our Smart Link Mapper view. And this is actually going to be a lot more clearer and precise on the information presented to technicians and staff and so forth. So we can see here that because we ticked our launch lead option on our settings, it's actually removed our launch lead from our test, which is what you want to do, because remember, a launch lead is essentially a tool. It's not part of the fiber you're testing. So the 0 meter mark starts after the launch lead. We've then got our 4 connectors that we've tested. We've got our receive cable on the far end and our end of fiber as well shown. We can see that there's 2 serviceable connectors here shown in green and 2 failed connectors in the center shown in red. Summary of the link total is shown here. We can see that it's failed with a red X, and that's probably due to the average loss per dB per kilometer of 4.22. Remembering for single mode fiber, the limit's 1, and you can typically expect 0.3. Now we do have events along the fiber, which obviously increase that, so we need to factor that in as well. And then because we've got 2 failed connectors here, we've got alarms shown at these 2 locations, and it's probably a bad or dirty connector. So moving on, we're just going to, if you've got a touch screen here, you can just touch on a particular connector to get more information on it. We can remember those fail thresholds I talked about earlier. We can see that the fail threshold here is shown. So anything over 0.5 dB of light loss is going to be a fail, and in this particular case, it's 0.315, so it's serviceable. On the other hand, this next connector along, once again, the same fail threshold that we configured earlier, but now it's 0.575, so it's over that fail threshold, and as a result, it's failed. Now, excuse me. So that gives us a full summary of our report that we can customize and move through on our Otdr. But now we've completed our test and we want to provide a report to our management. We hit that fast report button on the right-hand side of the screen. That brings up this report, PDF report automatically generated. We can see up the top, it's got all the configuration settings that we've talked about. And this is why I talked about making sure that your location is accurate and your fiber ID and details are accurate as well. So that will be automatically populated up here. And if you've got the wrong details configured on your Otdr, when you come to the end of the day and you're downloading your 10 or 15 trace reports, it's going to be hard to sort them out. Your details for your unit and your test configuration is shown in the next portion, and then your Smart Link Mapper view. Now in this instance, this particular report was only done on a launch lead, so there's not much information here other than the start and end of the fiber. We've got our trace of that particular launch lead shown as well, and a link summary of everything that occurs along that particular link. Now, because we also turned on the inspection probe capability, we've actually got the end faces shown of each fiber, so we know that they've been inspected and clean and ready to go as well. All right, that concludes this morning's webinar on fiber optic tooling and test equipment for enterprise applications. Feel free to get in touch if you needed any further details or information. More than happy to help. Thank you very much.